This problem is a basic nested for loop problem. It has several aspects to it that we need to inspect. So let me copy and paste this into MATLAB and discuss the problem before even looking at the possible answers. The first statement clear here is, of course, just to make sure that in case we've already created a matrix M previously, that we clear that out, because we might get a surprising output in MATLAB if we didn't use that clear command. And I'll give an example of that towards the end. The second line here sets a variable named counter to 0. The third line is an index for j, and j goes from 2 in steps of 2 to 4. So it's the same as writing 2, 4. And this goes from steps of 1 from 1 to 3, so it's the same as 1, 2, 3. And then we have these two statements, which are going to be repeated. Now, a few things you could notice here right away before even expanding this out is that each time we do something to this matrix M, right after that we're going to change the value of this variable named counter. So it started out at 0, but each time we modify M, immediately afterwards we're going to modify that counter variable. And so we know this matrix is going to have elements that are going to change. Another thing we can find is that M and Ij, so the I range, which represents the row in this case because I is the first argument to the matrix M, is going to have values of 1, 2, and 3. So we expect this output matrix to have 3 rows. The J is the second argument of the matrix M, and therefore it represents the columns. And the only columns that we're going to modify are columns 2 through 4. So immediately you can think, well, what about columns 1 and 3? Well, it looks like we never modify them, we never do anything with them. And so we would expect that matrix to have the first and third columns to be zeros. All right, let's look at possible solutions here and see how far we can get. Well, actually, the only one that satisfies that constraint, where the first and third columns are all zeros, is number C, or letter C. Now let's see how we get values in that matrix. And we'll do this by the standard method by which we split up this for loop. And now I'm going to just take this, just because it's easier to read, do this and this. And the way this program reads is that we should set j equal to 2, do everything that's highlighted. Then we should set j equal to 4, and then do everything that's highlighted. And so writing that out, we have j is equal to 2, and then everything that was highlighted is here. And then we set j equal to 4, and then we do everything that was highlighted. So we've expanded out that outer loop, and now we need to expand out this loop. And we have to do these commands in the highlighted commands, we need to do that 3 times. Okay, so now we need to expand out this loop. All right, now we need to expand out this middle loop. And we do that, we need to set I equal to 1, 2, and 3. So we'll do I is equal to 1, and then we're going to do those 2 lines down here. And then we just repeat it. I equal 2, I equal to 3. And this is the same thing as what I had just expanded, so I can do that here. I'm just going to copy and paste this. And now I have just a set of statements that I need to evaluate, and so I can just plug in values. So I'll do this. Last value of I defined was 1, last value of j defined was 2, and the last value of counter is equal to 0. So everything from 12 on down is the same thing as what I did up here. I guess technically to make it identical, I should do a clear statement here. So I have m of 1, 2 is equal to counter. The last value of counter was 0. And then now I have counter is equal to last value of counter plus 1. Last value of counter was 0, so now counter is equal to 0 plus 1, which is equal to 1. Then I just repeat that process. Last value of I defined was 2, last value of j defined was 2. So row 2, column 2 is going to be the last value of counter defined, which was 1. And then now we're going to make counter is equal to counter plus 1, which is equal to 1 plus 1 is equal to 2. And now we can, again, just read off values. We have row 1, column 2 is equal to 0. Row 2, column 2 is equal to 1. And row 2, column 2, row 1, column 2, row 1, column 2 is this guy, is equal to 0. Row 2, column 2 is equal to this, which is equal to 1. And then I can just repeat this process to figure out what all of the values in the matrix are. All right, and so when you encounter a problem like this, I want you to think about the different variations and try them, see if you can solve them. So one variation would be counter is equal to 10. What's going to happen? Well, you work that out here. This is going to change to 10, and now the calculation here is going to change to be equal to 0 plus 10, so it's equal to 11. Now it's 10 here, so it's 10 plus 1, which is equal to 12. And I could also ask you what the final value of counter would be. I didn't in this case, but we can just look at this and figure it out. In this particular case, if we started with counter equal to 10, you can see that here we incremented it by 1 to 11, 12. We're going to increment it here to be 13. Here is going to be 14, 15, 16. And so the final value of counter would be equal to 16. And now you can probably see why we called it counter. We just gave it a descriptive name because this is essentially counting the number of times you put something in the matrix. So that's one variation, is changing counter equal to 10. Another variation is you can ask what happens if you reverse this order. Well, if you've expanded this out, now we just need to reverse this, reverse these steps, and all of these steps we're just plugging in values. So we just reverse these steps and plug in values. And then we would have to do that later on down on the bottom here. Another variation on this would be what would happen if I reversed j and I. Well, it looks like everything here is the same, except I just have j and I here. J and I. J and comma I. And if you want to look at what happens, so let's just look at this to make it match the original problem. And again, I encourage you to make these little modifications, try to guess what's going to happen, and if you get the wrong answer, then work it out longhand like I did below here to see what you're going to get. And as you do that process over and over, you'll begin to build an intuition as to how these things work. So let me have this be similar to the original problem. And now the only thing I've changed from the original problem is I've swapped the j and the I. And I can use the logic that I had earlier to figure out, well, in this case, we're only going to be talking about rows 2 and rows 4. And so if I execute this, I would expect rows 1 and rows 3 to be 0. So let's do that here. And sure enough, I get rows 1 and rows 3 equal to 0. And this is, let me just explain a reason why I always put that clear statement in here. Suppose I was tinkering around and I said m of 1, 1 is equal to 99. And then I cleared the screen here, maybe clear console. And then say the student was doing that, they entered that information, and then they said, let's run this. And after running this code without the clear statement, I would say, I expect the first row and third row to be 0. And then if I executed it, I would get the first row having a 99. And based on inspection of this, I wouldn't expect that. But what has happened is that I've modified that matrix, and it's off the screen where I've made that modification. And so I've already pre-modified that matrix M to manipulate this value, and this value was never touched by this code. And so it just stayed the same. And so that's why I always put that clear statement. If I do that here, clear the console, paste, now I get what I expected. And then the other variations on this, you could ask what would happen if, instead of having something along these lines, if I had this. Now you can read this program and you could say I set counter equal to 1. I'm doing this statement a number of times, and I'm going to do this statement actually 6 times, because there's 2 elements in this array, 3 elements in this array. 2 times 3 is 6. And you can verify that by looking at what I've done down here. I'm populating the matrix with a value 1, 2, 3 times for j equal to 2, and then 1, 2, 3 times for j equal to 4. But now in this case, I never modify counter, and so between here and here, nothing has changed with counter. So when I execute this, I would expect counter to still be equal to 1. So counter stays as 1. And so this is just kind of a distraction kind of question. I could ask you, what are the final values of m and counter? And if you were memorizing the fact that counter gets incremented by 1 and it gets incremented as many times as you do this, you might say, well, the final value should be 7. But the fact is we never modified counter in here, as we have done in previous problems. So again, it's a matter of just knowing the rules of how you expand out these loops and not necessarily memorizing certain problems that we've done before. It's only remembering the steps that we use, the basic steps. Okay, and let's try to do this one without writing it out fully longhand. So fully longhand, we would have to do something like this. I'm going to just leave this here, or delete that, and then copy and paste. And so the longhand version of what's up here is this. And without even doing this, let's see if we can inspect what's going to happen. The first thing we're going to do is set j equal to 2. So this is going to be 2, and then we're going to vary I between 1 and 3. So row 2, column 1 is going to have the value of the column number, which is 1. I'm going to do row 2, column 2, so 2 comma 2 is equal to the column number, which is 2. So we expect it to be increasing from left to right as you go across a row.